Now, since I came to Plymouth, there was this new kid on the block being talked about by Plymouth Marine Laboratory. Now, the great thing about being in Plymouth is you've got Plymouth Marine Laboratory, you've got the Marine Biology Association, you've got all this history and brain power all focused on marine sciences. And it's a resource that's very, very useful, especially for people at my level of my career, where we can just wander up and say, what do you think about this and what do you think about that? It's good. And what they're very concerned about is the fact that the oceans are acidifying because of the amount of carbon dioxide that we're pumping into the atmosphere. This is a graph showing the amount of carbon dioxide that's being pumped into the atmosphere, and you can see it's inexorably going upwards and upwards. There are sometimes things that happen geopolitically that slow that rate of emission down a bit, but things soon pick up again. And at the moment, we're exceeding all of the predictions for what that CO2 emission would be, because countries like China and Brazil are really booming. So they talk about an economic crisis, but it's not a global economic crisis. It's one that's affecting Europe maybe, but not the BRICS countries. And where does this CO2 come from? Where does it go? Well, about 0.9 petagrams of carbon, which is an unbelievably huge number, comes from cutting down forests and burning forests. And the other chunk, the 9.1 petagrams of carbon, comes from burning fossil fuels and making concrete. If you add those two sets together, we're producing about 10 billion tons of carbon per year, which is a hell of a lot. Half of that stays in the atmosphere, and a quarter goes into making trees, it's sucked up by trees and plants on land, and a quarter ends up in the oceans. And that quarter translates to 24 million tons of carbon dioxide every day are entering the sea. And that's a problem because carbon dioxide is a reactive gas. It reacts with the chemistry of the water to form a weak acid called carbonic acid. And that's why this term ocean acidification has come onto the scene. It was only invented, this term was only invented in 2003, and I'd only heard of it in 2006, but it's very much something that lots of people are concerned about now, especially the research scientists. This is a very famous graph at the top there, which is data that's been collected in Hawaii. The solid black line that wiggles and goes upwards is the atmospheric concentrations of carbon dioxide. And you can see it's going up every year. The wiggle is because carbon dioxide is sucked up by trees to make leaves in the summer and then released again into the atmosphere when those leaves drop off and rot. So that's the wiggle that's going on there. But nevertheless, it's going up year on year, and when you measure the amount of carbon dioxide that are in the seawater, at the surface of the water around Hawaii, they're going up as well. There are only 3 long-term monitoring stations that have been recording the amount of carbon dioxide being absorbed by the sea from the atmosphere, and those are those dots on the map on the left there. Those dots are these different coloured graphs, so there's green, there's blue, and there's red, and they're all showing the same trend. Okay? CO2 levels are going up, and the pH of the water, because carbonic acid is formed, the pH of the water is going down. Now, don't leave this lecture theatre thinking that the seawater is going to be unsafe to paddle in because it's like a battery acid or something like that. If you look at the scale, you're coming down from pH levels of about 8.15 to pH levels of 8.05. Okay, so it's still remaining an alkaline solution, and it will do no matter if we burn all of the fossil fuel on Earth, chop down all the trees, just completely burn all the carbon there is, and chuck it into the atmosphere. That will never drive the CO2 levels high enough to make seawater acid. It will never get below pH 7. Okay, so it's not going to be an acid solution. And this is this scale of pH, which is a logarithmic scale, and it makes it a bit confusing to understand. So I'll translate it in a minute to a scale that makes more sense. But if you go back in time to 1800, the pH of the water, on average, at the surface of the oceans was about 8.2. Now already, it's dropped significantly, and I'll say why it's significant later. And by the end of this century, it will have dropped even further. If you translate that into what pH is really measuring, it's the amount of protons in the water, these H+ ions, which are corrosive. Okay? The H+ ions are highly reactive, and they dissolve things, but they'll dissolve shells, they'll dissolve corals. Actually, I meant to pass this around before, because this is a coral, the type of coral that we recorded off Rockall, that is from off Rockall, and it's made of a substance called aragonite. And aragonite is a type of calcium carbonate that's attacked by protons in the water. And you don't have to get below pH levels of 7 for this stuff to corrode and dissolve away. It all relates to the saturation states of carbonate in the water. So that's what's forming these giant coral reefs in the Arctic, for example. Okay? And we're concerned about this stuff because as the water becomes more corrosive, it's inevitable that that material will dissolve away unless the organisms can protect themselves from dissolution. When the coral is alive, it covers its skeleton with its polyp, but when it's dead, that skeleton is exposed and then dissolves. So yeah, we've already seen a 34% jump in the acidity of the water around Plymouth and elsewhere in the world, and by the end of the century we're going to be up well above 100% increase in the acidity of the water. So that's a big deal. And I've noticed Richard is in the audience, who is a geologist, and he understands these backwards graphs where geologists basically turn it around and say, going this way along the x-axis, you're going back in time. Okay, so this is going back in time, 800,000 years back in time. And for that last 800,000 years, we know from the geological record that the pH of the water has always been way up there where those red lines are, 8.15, 8.3, that sort of level. No matter how much ice has been formed or melted, it's been wobbling around for 800,000 years up at that level. And you see which way the graph is going now, straight down, because that amount of CO2 in the water is really building up. So that's the amount of CO2 on the right-hand side. Increasing the blue line, the pH of the water, the red line, is going down. And as far as we know, this is unprecedented. It's never happened this fast before. What we're doing is geologically unique by chucking all that carbon into the atmosphere as fast as we possibly can. And the rate of change is the important thing, because, well, for technical reasons it's important. There are periods in Earth's history when CO2 levels were higher in the atmosphere than they're going to be this century, but that happened over such a slow time that the chemistry of the sea was able to equilibrate that problem. That isn't happening at the moment because it's happening too quickly. Now I thought, well, corals are clearly a concern because they're made of aragonite. And there are coral gardens right off the coast of Plymouth. This is just off the breakwater. No, it's not. It's the Persia, I think. Persia, yeah. Well, it's not far from the breakwater. It's South Devon coast. Absolutely festooned in this beautiful garden of corals. And those corals inside their skeletons have these needles. Why am I pointing at that? You can't see that. Those needles on the top right-hand corner that are made of chalk. And what we did was get students, master students, to take organisms like these corals, put them into buckets of seawater, and bubble carbon dioxide through those buckets to see what would happen. And in this case, for example, those needles of chalk would simply dissolve away, and the whole sea fan would become much more floppy. But that scientifically isn't very satisfying, because you're suddenly getting a coral that's used to living in the sea, shoving it in a bucket, then whacking loads of carbon dioxide into the bucket to see what happens. And that doesn't really tell you what's going to happen over the long term, gradually over the course of the next 5, 10, 15 years, as acidity level gradually increase around Plymouth. So what we decided to do instead is to go to areas that have got naturally high levels of carbon dioxide to see what the seabed looks like and what organisms can live in those areas.